Hi, today is the first class on this course that we have under the NPTEL program called Combustion. So we will just start with the course outline. The first thing that we will do is a little bit of thermodynamics, but what are we going to get out of here is essentially the adiabatic flame temperature. Number 2 is we do some chemical kinetics. This is going to tell us how fast I'll explain these things as we go along. Number 3 is some mass transfer definitions. So this will lead to the Fick's law. Number 4, conservation equations. So here the most important thing that we will bother about is species mass conservation, and then we will also worry about mixture momentum, mixture energy, and what's called as multi-component diffusion. All right. Then we will go through what's called as Swab-Zeldovich formulation. Number 6, we now do what's called as Rankine-Hugoniot relations. 7, premix flames. And diffusion flames. So here we do two things. One is what's called as the Burke-Schumann problem, and then we will do droplet burning, and then we do a few more things, which is, first of all, we do partially premixed flames, and then we do turbulent flames. So that means if you now go back, we can now realize that these are laminar. So here we will do a overview, and this would be both premixed and diffusion flames, and let's say we do a little bit of solid propellant combustion, spray combustion, 13 detonations. In this, essentially we restrict ourselves to what is called as the ZND model, and lastly we do some combustion instabilities. Alright, so this is like what is planned for about a 40-hour lecture, and this is a little bit ambitious for a 40-hour lecture. We will try to squeeze as much as we can, but if we can't, we will let it overflow. Alright, so we may not really finish everything by about 40 hours. That's the first thing. The second thing is, this is a course that is pitched at the level of senior undergraduate to a first introductory graduate level course in combustion. Alright, so that's kind of like, we are not talking about very advanced level combustion. At the same time, we are not talking about something that is too introductory. Alright, so we have to get reasonably mathematical here to get the equations in shape. Therefore, somebody wants to actually get into some kind of a computational approach or a theoretical approach, you should be in a position to do this from this course onwards. So that's essentially how this is shaped up. Alright, with this we should now start thinking about what we are getting into. Combustion, what does that mean? Right, so what does it ring in your minds when you think about combustion? Obviously it's something like a fancy technical sounding term for something that we are very familiar with in our daily lives, essentially the process of burning. If you can say that, you wouldn't be too far off the mark. Okay, you would have covered most of what we come across. Then the question is, what is burning all about? Alright, so we have to first of all understand these things in simple English, right. So combustion is like, let's say, approximately the process of burning, and then we have to think about what is burning all about. So we now start thinking about what we are familiar with when it comes to burning. Okay, what are the most familiar situations when you come across burning? Anybody? No, like practically, when do you come across burning? Matchbox. Okay, anybody else? Stoves. Okay.
Forest fire.
Flash fire.
Forest fire.
Furnace fire. Forest fire. Oh man, he's a jungle guy. Okay, so forest fires. Okay, then jet engines. This is like an aero guy. Okay, so he wants to go jet engines. Okay, so let's start listing these things. So combustion is like process of burning. So example, matchstick. Okay, what else was the answer? Say stoves, forest fire, and jet engines. Okay, anybody else wants to say anything more? IC engines, rocket engines, jet engines. Okay, fine. So IC engines. Okay, anybody else wants to say anything more that you come across? Candle, huh? So somebody is very romantic there. Okay, so candle flame. Okay, candle flame. So now you see we are now getting into some jargon. So on the one hand we have something called a flame, on the other hand there is something called a fire. Okay, these are things that we come across. What do they mean? In plain English, flame and fire, are they different or the same? Can we say that?
By flame we mean steady fire.
Steady fire.
Yeah, it's fire which is steady, not increasing.
Okay, so well, in technical combustion literature even unsteady flames are flames. Okay, and fire is typically something that spreads more or less in an uncontrolled fashion, but you could have essentially something like turbulent flames that are there in furnaces, for example, like very large furnaces or oil fired furnaces again. Okay, or coal furnaces. Many of these things actually have very large fires, right? So or what we think of them as fires, but they are also typically classified as flames. But the steady flame that you call as flame is something that you can for example associate with like a candle. So you light up a candle and it just stays steady unless you now see how big that candle is or how long it's been burning, right? So for example, let's say you're burning the midnight oil for an exam the next day, and then you had a power cut and you had to light up the candle to keep going on. All right, somewhere through the wee hours you're going to now have the candle begin to flicker. What's going on there? Has the flame become fire? Huh?
We have a main flow which is apart from the actual candle thing.
What's going on is you now have a buoyancy driven flow, that is like the candle vapor mixes with air and burns and produces products that are hot, and because they are hot they move upwards and they begin to actually oscillate because you're now beginning to have some sort of a instability in that flow of hot gases that percolates back to the flame. Okay, and the flame begins to start shaking. Alright, so it's an unsteady flame there at that time. It's not necessarily fire yet at all. Okay, so what are we then, if you want to now analyze this kind of situation, so that we now just talked briefly about how a candle works, right? But what happens in a jet engine, for example? Let's say consider the other situation. Okay, so if you now look at a candle, let's suppose you now can draw a wick over there, and you now have a flame, and this could be moving back and forth, okay, in an unsteady fashion. But essentially you're having a wick in which you now have fuel coming out in vapor form ultimately, and then mixes with the oxidizer that's around, and then you now have a flame there. Okay, but if you now look at a jet engine, let's get a little bit more specific. Maybe we talk about what's a favorite jet engine for you? Anybody? Turbojet. Okay, so say turbojet. Now of course I'm interested only in the combustor of the turbojet. I'm not interested in the compressor and the turbine and so on, so therefore I'm going to draw some sort of a schematic of how this looks like. Oops, let's see how this comes about. So you now have a fuel injection and then a swirler over there, and then you have a flow that's coming out. I made a mistake. Let me just redo this. So let us say and then I had a swirler box into which, and they have an atomizer, and then yeah, right. So I had a airflow come over here. This is fuel, and you had the air come also on the sides. So this is like what's called as primary air, this is like secondary air, that's like dilution air, and so on. So you now have a flame that is sitting there, okay, highly turbulent flame, right? Right. So what have we been talking about for the basic elementary processes that constitute combustion? So to give you an example of the kind of answer I am looking for one thing, you have a flow. You have a flow of air through this, okay, and then you have a fuel injection. That means the fuel has to flow through the fuel nozzle and get out there, all right. And then what do the fuel and air do? Not yet. They mix, right? So one of the things that we are talking about is flow, the other thing that we are talking about is mixing, and the third one is
Reaction.
They ignite and then there's a reaction.
React.
There is a chemical reaction that goes on. Alright. So effectively we are talking about three major things that we should be keeping in our minds when we are looking at combustion. So combustion basically means flow, mixing and chemical reaction. Alright. So in little bit more technically sounding jargon, we could say this is like convection, diffusion, right, and reaction.
But is convection always necessary?
Well, we are talking about the three basic things. Okay, so you could argue, well, I could have convection and diffusion. Would that be combustion? Probably not. Okay, I'll come to that next. Then can we have diffusion and reaction? Would that be combustion? Maybe yes. Can I have convection and reaction? Would that be combustion? Maybe yes. So we are looking always at chemical reactions being present when you're talking about combustion, right? So from the question that he asked, I kind of take what I want. Okay, so what kind of chemical reactions are we talking about when you are talking about combustion? Any chemical reaction? Exothermic. What did you say?
Oxidation.
Oxidation. What else?
Fast oxidation.
Fast oxidation. So there is a person back there who is not just sufficient for him to be slow, it should be fast. Why? Huh? That will be an explosion?
So that there is a chain reaction. Continuous.
Otherwise what happens? Can't you have slow reactions that continuously happens?
Should be extinguished. Flame will be extinguished.
Why? Why would a slow reaction cause an extinction?
The heat would be convected.
Usually slow.
You?
The heat would be convected out before it preheats the mixture.
The heat would be convected out if it before it gets preheated. So how does the heating happen in the first place? Right, so you have a exothermic reaction that is happening, and the heat could be getting convected out. That means it gets washed away, okay, before it can preheat what?
Preheat
The reactants to get up to this temperature at which they can react. So how is this happening? Why?
We use a burner.
Yeah. But how is it actually getting heated up? So let's say I had a flame right in front of me. Okay, how do I know that without seeing? Because the air and fuel don't have eyes to see, right? But how do they know that they are getting into a flame zone? Radiation and convection, conduction. So essentially, what you're talking about is some kind of a heat transfer that happens to the reactants in order that they actually get heated up to the flame temperature, where they get in and start participating in reactions and constitute the flame, right? So if you now have a reactant flow that's coming in, it has to get heated up and get into the flame, and then the flame itself happens, and when the flame has happened, its job is to actually heat up the reactants that are further coming in so that they will come and participate in the flame. When the flame is there, it now produces products that will go away, right? So what is a flame now?
It is a combustion zone.
That's like twisting yourself, right? Then I'll ask you what's a combustion zone, and you can say it's a flame, right? Can we speak English like we don't know anything about flames or combustion?
The place where the reaction takes
The place where the reactions are taking place. Alright, so a flame or a combustion zone is nothing but a place where the reactions are taking place, nothing more. You see? Now what has happened is, so let's just record this. So this could, now the diffusion here could also mean heat transfer, okay, predominantly conduction. That's the reason why I am writing this under diffusion, okay, conduction, heat transfer, plus radiation, alright, plus some radiation. So for example, what is meant by radiation? For example, you can see the flame. If it is like a diffusion flame, it gives out light a lot more than a premix flame, like an orange flame that gives you a lot more light. Back in those days they used to use combustion for lighting, okay, at night. So that's essentially coming out by radiation, but most of the energy that is being consumed is released in heat rather than by light, so it's not significant unless you are looking at some specific situations which we will talk about as we go along. But you look at the factor, the fraction of energy that's involved in the radiation heat transfer versus the conduction heat transfer.
No, and my question is the light being generated is because of the heat.
The thermal. Fine. Let's not worry about how the light came up. Okay, so we have this going on, and so we have the convection going on and the reactions going on. We also notice that these should be fast exothermic. Okay, and typically you want to have fast exothermic chemical reactions mainly when you deal with gaseous reactants, because when you now want to have reactions happen, molecules have to collide. Okay, so if you now have two solids where you don't have a mobility between the molecules of the solids, it's very difficult for them to collide in the first place. Okay, to a lesser degree similarly with liquids, but with gases, and as you pressurize more and more, okay, the molecules can actually interact, bombard against each other much more, so you're able to actually get fast chemical reactions mainly with gases. Therefore most of combustion, not all, okay, most of combustion is essentially happening in gas phase. Now does that make sense? I would like to counter that by saying no, most of the combustion actually happens not in the gas phase, because I use petrol in my car, I use the diesel in my in a bus, okay, these are all liquids. I could be burning wood or coal, which are all solids. Yeah, so these are typically what are used for getting energy for transportation or otherwise. What are we talking about? Gaseous. They have to vaporize because they just simply don't withstand the temperature in the first place of the burning, so they vaporize. The actual combustion reactions that are happening in the gas phase most of the time for most applications. Alright, so those are the ones that are significant. So what has happened in the last let's say half an hour is we have made tremendous progress. Okay, we were just barely beginning to spell the word, and here we are talking significantly about convection, diffusion, chemical reactions. So what this means is you need to know fluid mechanics, okay, you need to know transport phenomena, and at least a bit of chemistry, right? So at least a bit of chemistry. So you need to know a minimum of 3 basic subjects before you can actually get to doing combustion. Okay, so no wonder you can't do this too quickly in your career. So you have to wait until you are like a senior undergraduate or a, let's say, a starting graduate student before you can master some of these things to some extent before you can actually do combustion. Alright, good. So then let's look at what we are supposed to do. Right. So the first topic is actually speaking thermodynamics applied to combustion. Okay, so we are not going to really do combustion itself, we are going to basically be doing thermodynamics, but applied to combustion. The goal being we will now get what's called as the adiabatic flame temperature. That means the best estimate for the temperature without any heat losses is essentially what you're looking for. All right. And when you now look at the, and this is not going to tell you how fast things are happening. Thermodynamics always talks about changes, okay, from like an initial state to a final state, or state 1 to state 2. In fact, initial and final are even misnomers to be used because they have a connotation of time before and after. Thermodynamics just doesn't care about time at all. It's only talking about a change from state 1 to state 2. All right, and of course the direction of increase in entropy is what's deciding what the direction of change from path 1 to state 1 to state 2 is. Okay, that's all thermodynamics can do for you. But if you want to now start worrying about how fast these exothermic chemical reactions are supposed to happen, then you have to do chemical kinetics. There's also something that you're familiar with. Okay, but we will go through this and we will bring in some notation that is sort of like algebraic, or trying to algebraicize chemistry, if you will. Yeah, so we will try to do that, and plus also talk quite a bit about the details of chemical kinetics, where they play a role and so on. Then we have to worry about mass transfer definitions. This is picking up a little bit on transport phenomena, ultimately leading to what's called as Fick's law, that's involved in mixing two species. So when we talk about species, that's like a new term. Okay, we are not talking about biological species, but we are now looking at chemical species. Okay, so chemical species simply means a particular compound or an element. Okay, so we want to now treat them in an algebraic sense, call them like X or Y, and then we want to call them a species as opposed to compounds and mixtures or something. So then we will be in a position to actually look at conservation equations. What we will now find is there is a need for something called a multi-component diffusion equation, which is the multi-component counterpart of Fick's law. Because what we will note is Fick's law holds good only for a what's called as a binary mixture. Okay, that means you can have only two species in a mixture, and if you want chemical reactions to happen between them, that means one of them should be a reactant, the other one should be a product. Okay, it's not like two of them react with each other, no. Because anytime you have a bunch of reactants, you also have to reckon with products, right? Therefore that's a very restrictive situation for you. So we will have to look at how the multi-component diffusion equation works out for a truly multi-component mixture. Multi-component simply means more than binary, more than two species. Schwab-Zeldovich is a new term for you, except I want to point out at this stage Zeldovich is like a father of combustion. I should point out at this stage a little bit of historical background. Okay, combustion, how old is it?
1.5 million years ago.
Sorry?
1.5 million years ago.
1.5 million years ago. Okay, were human beings there at the time?
Yeah.
They were? Okay, so they discovered fire?
Yeah.
That's what you're talking about.
No. Yeah, the
So you quickly get into this confusion. Like, do we have to consider combustion that happened before human beings discovered it or after? Huh? So it's been around for a long time. So right from the Big Bang, maybe, huh? If you want to call that combustion. Now I want to also point out that we are restricting ourselves to chemical reactions here. That means we are looking at exchange of electrons from atoms and molecules. Okay, whereas we are not necessarily looking at nuclear reactions, where you will have the nuclei participate in the reactions as well. Now these days, for example, you look at the hotel plenary lecture at the 2006 combustion symposium at Heidelberg by Ed Law. He would now say all reacting flows, including biological reactions, should be combustion. okay, but that is not the conventional sense in which we know combustion. So typically we will be dealing with chemical reactions, alright. So I do not know if Big Bang included only chemical reactions or also other things, but fundamentally we can imagine that burning happened even before human beings were around, but one of the first things that human beings discovered is fire, okay, maybe before even inventing the wheel, alright. So it has been around for a long time. What do we know about the science of combustion? So this is technology. So this is a classic case where technology precedes science. You do something, figure out how it works, right, but do not know why. That is the difference between how and why, yeah. So what about the science? What has been the state of combustion science over a period of time?
We pretty much can identify lots of reasons why things happen, and we can explain lots of phenomena, but not completely.
That's like the progression of science, all right. But specifically the combustion science, what have we known about combustion science over the period of time? For example, when you now look at how mechanics progressed, you know that with the advent of Descartes there was some progress, with the advent of Newton there was some progress, and so forth, all right. So what do we know about, let's say, combustion science?
We made a good progress in premix, laminar premix flame. Diffusion is
when? Historical.
When around, I don't know when.
Right. Okay, so what has happened is bulk of the science of combustion had to wait until significant progress had been made in any of these three fronts, right. That is fluid mechanics, transport phenomena, and chemistry. It turns out, for example, if you look at transport phenomena, all right, so you look at mass transport, momentum transport, energy transport, right. So you look at momentum transport, this is due to a flow being viscous, okay. Newton figured this even in the later half of the 17th century or earlier part of the 18th century, but Fourier was the one who figured out in the earlier part of the 19th century the heat conduction, okay, that is the energy transport. It took further out for Fick to figure out the mass transport. So mass transport actually happened quite late in the game, okay, and then we had to worry about multi-component diffusion and so on. So it took quite a bit of time for this to happen, and we are now already looking at later part of the 19th century, okay. Chemistry, so for a long time it's been alchemy, okay. So chemistry also started making strides only in about the 19th century, later part or thereabouts. Putting all these things together, it's only in the late 19th century that any combustion science ever pretty much happened. Of course you can argue about this significantly, but it's very late in the game when compared to lots of other classical mechanics related sciences, okay. Bulk of the progress in combustion science has pretty much happened in the 20th century, okay. We are still very early in the 21st century, so we can't compare the bulk now with what happened in 20th century. So 20th century is where bulk of the progress happened, and interestingly towards the second half of the 20th century you now made strides in all three fronts in terms of approaches. One of them is mathematical, analytical, okay. There some progress was being made in the early part as well, but you needed significant mathematical tools like asymptotic expansions, perturbation methods, and so on, which matured through application to boundary layers and all those things earlier on, and then they were being applied later on in combustion. And computational combustion has seen a huge investment of time and effort in the later part of the 20th century, and similarly in experimentation there is like a big emphasis on laser diagnostics that has happened, because we are essentially looking at things that are happening at the molecular level, all right. The other thing that happens with combustion is the multi-scales, okay. So the fluid mechanics part of it, that is the flow part of it, happens over a fairly large length scale, okay, it has to now go from this end of the combustor to that end of the combustor, whereas the mixing and the reactions happen in much smaller regions, and even in these smaller regions the mixing happens in a smaller region in a macroscopic sense, okay, but the reactions are happening in that region in a microscopic sense, okay. You have to get molecules to mix with each other. That means we are now trying to transcend between here and here, we are trying to transcend from a continuum framework, okay, to a molecular level framework. That's a little bit hazy, right? So we have to figure out how to handle these things together, yeah. So fundamentally you are now having a multi-scale problem here, and therefore doing combustion calculations or diagnostics is difficult. You have to keep the big picture of the flow at the same time as looking at the molecular level processes, okay. That's very difficult, and therefore combustion problems have eluded solution for a long time. It takes a lot of effort to get into combustion. This is not to discourage you, this is to actually encourage you because this is challenging stuff. Plus I also want to point out that looking at the future, okay, combustion is becoming very significant, okay. It is becoming significant from 2 counts. One, we have a energy demand that is growing in the human civilization, and most of the energy in the foreseeable future of let us say the next several decades, like in our lifetimes, is going to still come from combustion energy, okay, either fossil fuels or coal or some other things. And of course when we are done with burning everything that can burn, we will still find something more that will burn, okay. I can't believe that combustion will come to an end in about 70 years or something like that, when it actually started, when we don't know, right. So it would happen, right, and it's going to happen more and more in the next few decades, next several decades in fact, okay. So we need to be solving combustion problems for tapping energy from different sources. As I said, fossil fuels, coal, as well as now biomass, okay. So for example, that's like a new renewable energy that you can think about. Second thing is the pollution and environmental problems, that is like global warming and so on. This is also caused by combustion. So on the one hand combustion is required, on the other hand combustion is bad. So it requires combustion engineers for you to engineer your combustion in such a way that you get what you want and you try to avoid what you don't want, okay. So that's the engineering that we have to do, which means the combustion research and the engineering that we do now should be a lot better than what has been done before, okay. That means we need smarter people working in this area, so because it's highly challenging, and the practical challenges are a lot more. Therefore let's continue with where we were, okay. Somewhere in there in the first half of the 20th century, we now have Zeldovich show up, okay, and he is like a leading figure in combustion. In fact, at every combustion symposium they give the Zeldovich medal for lifetime achievement for a combustion researcher. That means like they give the best medal after Zeldovich, okay. We do the Rankine-Hugoniot relations. Those of you who have done gas dynamics would have come across at least the Hugoniot part when you're dealing with shocks, alright. So what we want to try to do is something similar, which means we now try to deal with flames as if like they are shocks, okay. What does that mean? It's like we want to look at them as like surface of discontinuity. So you have reactants on one side, products on the side, don't worry about what's happening inside, okay. You just have a discontinuity between the two, separated by the flame. Can we analyze the situation like this without getting into the flame? And we will find that it's not, at the end of it we will find that it's not possible to avoid getting into the flame, and therefore we will get into the premix flames. We will spend quite a bit of time doing this. We'll try to find the laminar flame speed, and then we will look at flame stabilization issues, flammability limits, ignition and quenching, all these kinds of things over there. How to treat flames globally when given a flame speed, and how the flame speed should be computed in the first place, flame shapes versus flame structure, and so on. So I would like to distinguish these things as we go along. Then we get into diffusion flames. So the name suggests obviously that when you now have premix flames, the reactants are mixed by the time they get to the flame, whereas in the case of diffusion flames the reactants are just mixing, right, as they are burning. So they are kind of busy mixing as they are burning. Okay, so that's what this is. And then of course there is like a standard problem that was published in the first symposium of the combustion, first combustion symposium, 1928, the celebrated Burke-Schumann paper. We will go through that, and then we'll look at further advances to this that has happened through years, even as late as like the 80s or 90s. And of course droplet burning is pretty important from a practical point of view, and it's also covered under diffusion flames. These are extra topics. Okay, so once you are able to do this much, then you have to get into realities. Like these are like a little bit advanced, so we will talk a little bit about these as we go along, maybe one lecture each or two lectures each and so on. Some of these are picked because I do research in this area. Okay, so we can only talk about what we know, right, so or what little we know. So that's what this is all about. So that's how this is structured. I also want to talk a little bit about the books that we want to go through. So let's talk a little bit about books. The first book that I would obviously look at is Williams. So this is combustion theory. This is, I think the second edition came out in 1984. I'll give you the publisher details and so on the website that goes along with this these videos, but effectively I want to talk a little bit about these books now. Williams is now the living father of combustion in some sense, because most of the advanced level graduate students couldn't have escaped his textbook. It is a little bit dense, it's difficult to understand, but you have to work on it. Okay, and you will reap rich rewards once you do that. A derivative smaller book was also written by Embel Linian. So this is it's a Spanish name, so you have to pronounce it, I guess, as Linian with all this tilde and a and this accent here, and F.A. Williams. This is fundamental aspects of combustion. This is around 1993 or thereabouts. I'll give you the specifics in the website. If you want to have light reading, I can suggest two books to start with. One is W.C. Straley, which is Introduction to Combustion, and this was around 1992 as well. And then there is an Indian author, H.S. Mukunda. This is Understanding Combustion. This is actually an IIT Madras publication, as a matter of fact. Then there are much more recent books that have come up. So recent textbooks, I would like to list about a couple of two or three. One of the most recent ones is C.K. Law. This is Combustion Physics. The second is maybe you can say Stephen Turns, S.R. Turns. I forget the name of the book. I can get back to you on that. Then there is a K.K. Kuo, which is Principles of Combustion, second edition. So these are more recent in the last 5 to 10 years, and these things are improving. There are a lot more books that are coming up, and but they typically, many of them focus on specific aspects of the science, because it's simply difficult for anyone to do all of combustion, and therefore they typically focus on one particular aspect. Like maybe one book would be more on chemical kinetics, the other book would be more on computations, and so on. Okay, so there is a lot of books that are there, but I would like to start with, maybe you can look at some of these. I will follow one or two of these books, and I'll try to point out which book I am following at a particular point, okay, so that you can go back and refer to it as you go along. With this, let's stop the introductory lecture, and we will pick up from the first topic the next class, okay, that is combustion thermodynamics, and look at how to calculate the adiabatic flame temperature from there on. Thanks.